All right. Good morning, everyone. Welcome to today's SNAPP seminar. We're very excited to have Professor Benjamin Van Roy from Stanford, and he's going to talk about reinforcement learning. So before we get started, quick comments about how we run this. If you have any questions, just post them on the chat box, which I'll keep monitoring. And Ben plans to have one or two pauses through midway through the talk when you'll get a chance to ask questions. And we'll have an elaborate Q&A session at the very end. So Ben Van Roy is a professor at Stanford. His research focuses on design, analysis, and application of reinforcement learning algorithms. And he has been very active beyond academia as well. He currently leads a DeepMind research team in Mountain View. And in the past, he has led research teams at a couple of startups, Unica and Innovis, and also at Morgan Stanley. He's fellow of Informs and IEEE, and he received his bachelor's, master's, and PhD all from MIT. His bachelor's was in computer science and engineering, and his master's and PhD were in electrical engineering. And today he's going to talk about simple agent and complex environment in reinforcement learning. So Ben, the floor is yours.
Thank you very much, Siva. Thanks for the invitation. It's nice to be here among so many old friends that I've seen over the years, including students who have come through Stanford. So this talk is on work I did with Shi Dong, who's a current student at Stanford, and Zhengyun Zhao, who's on the faculty at NYU. But I should say that when I say with, I mean Shi Dong did most of the work. How do I get to the next slide here? There we go. So, so reinforcement learning has demonstrated impressive successes in simulated environments. And the trend these days is to tackle increasingly complex simulated environments. Now, these success stories tend to involve massive simulations that generate enormous amounts of data that could take millions or billions of years of equivalent real-time interaction. Major advances in data efficiency are required to transfer this success to real environments. Here's a cartoon plot that was produced by a friend of mine, a roboticist named Martin Riedmiller, who plays with reinforcement learning agents. And it illustrates how long state-of-the-art reinforcement learning agents take to develop even rudimentary competence in simple robotics tasks like stacking blocks. The point here, if you do back of the envelope calculations based on this, is that it takes about a year of real-time operation to gain any reasonable level of competence, even with the simplest of tasks. So in this talk, I hope to share some thoughts on the possibility of designing agents where data requirements do not scale with environment complexity. Such agents may be able to develop competence in arbitrarily complex environments within reasonable time. Okay, so that is the thrust we're after here. Here is the reinforcement learning agent environment interface. In the general reinforcement learning, in the general framing of reinforcement learning, an agent interacts with an unknown environment through executing actions and registering observations. To keep things simple, let's assume that we're dealing with a finite set of actions and a finite set of observations. The interaction through time t in this general reinforcement learning setup is encoded as a history, ht, which is a sequence of actions and observations experienced through that time. Okay, so this is the framework we'll be working with today. It's very general. And I should mention, for those of you who have been reading the reinforcement learning literature, one thing you should take note of here is that I'm not making any Markovity or episodicity assumptions. Such assumptions are common in much of the reinforcement learning literature. And I view those assumptions as restricting to classes of environments that, for didactic purposes, that are special cases of environments in which people have been able to do some analysis and generate some insight. Okay, but that is restrictive if we're thinking of taking reinforcement learning to real environments. Okay, here's an example of an interaction with a real environment. You could consider a dialogue system. And in particular, you could think of each action in a dialogue system as being a message. Here, the agent is sending a message to the environment, saying, how can I help you? The observation from the environment could itself be another message registered by the agent. And this kind of interaction could continue over time. And the agent could learn how to, for example, be more helpful to individuals with which it interacts. To offer another example of an environment, you could imagine a queuing network. And for example, you could think of actions as being assignments of servers to queues and observations as being queue lengths at that time. Finally, for a sort of more complex but example that is of practical import is you could view the internet as a complex environment. So you might design an agent to interact through a typical computer interface, perhaps learning to accomplish some goal through its interactions, like fact-checking news or appropriately tagging that news, or teaching academic subjects to people. And in this case, the environment is becoming so complex that that the agent is bound to, the agent design is bound to be, it needs to be bounded, and there's compromises that need to be made in order to maintain a level of complexity in the agent that is much smaller than the environment. All right, so the field of reinforcement learning really addresses this problem of agent design. And the idea is to try to design an agent that operates effectively given the agent environment interface. And the kind of question we're hoping to shed light on today is whether an agent can be efficient across a very broad range of environments where the complexity of these environments far exceeds that of the agent. Okay. All right, and in order to focus the talk and anchor it around something pretty concrete, I'm going to present a particular simple agent that is designed for dealing with environments that are much more complex than it is. And this agent maintains bounded memory and per time step computation through tracking an agent state. Agent state really offers a simplifying lens into the complex environment and allows the agent to operate in this bounded way. Okay, now our agent is going to use an algorithm that is an optimistic version of Q-learning. So most people who have studied the reinforcement learning literature are familiar with the Q-learning algorithm. And so our agent will basically use a variation of Q-learning. And so people who have studied Q-learning should quickly see what the agent is actually doing operationally. All right, now a couple of things that we want to study here is the eventual performance of the agent. This is going to depend on how well aleatoric state can predict value. Now, I mentioned agent state. A component of that, as I'll discuss, is what I call aleatoric state. And aleatoric state is meant to summarize the agent's situation in the environment. I'll talk more about that later. The other thing we're interested in here is the data requirement, right? How long does it take to get to that level of eventual performance? And what we'll see is for this agent, the data requirements grow with the complexity of aleatoric state dynamics. Now, aleatoric state is something that the agent is maintaining in its mind that may not actually have that much to do with the environment. It might be much simpler than the environment. And so the key here is that the data requirements don't grow with the complexity of the environment dynamics. It only grows with the complexity of the aleatoric state dynamics. Okay. Okay, I should mention a few disclaimers here. One is that we don't recommend applying this agent. This agent isn't designed to be practical, and it can be improved in many ways. Okay. However, the point here is that the agent serves as a constructive proof that we can achieve particular things, and as a sanity check that there's a viable path here. That said, there's a lot of work in reinforcement learning that deserves that kind of disclaimer. But in this case, I think that the relevance extends further than a constructive proof. And in particular, the agent is designed with elements that are common across practical and successful agents. So the interesting thing is this agent actually shares some of those common characteristics. It's not purely a constructive proof that's completely different from what more practical agents use in terms of algorithms right now. Okay, so given that there's that connection with more practical agent design, this particular agent I discussed today, for which we can prove some interesting theoretical results, may offer a starting point to build a bridge between theory and practice in this area. All right. So on the practical side, maybe furthering this line of thinking can lead to more principled approaches to design and analysis of agents. Okay, so here's the outline of the talk. I'll start by discussing what I mean by agent state and introducing notions of reward and policies. And then we'll talk about the performance of the agent that I'll propose. After that, I'll actually describe the agent, and then I'll move on to some open issues. Okay. All right, so what's agent state? The agent state is everything the agent keeps track of and retains in memory, which it can use to select actions, to make decisions. And in many reinforcement learning agents, in fact, I'd say almost all I know of, are designed with an agent state that can be decomposed into three parts. There's an algorithmic state, an aleatoric state, and an epistemic state. All right. And the algorithmic state is stuff that the agent's retaining in memory that has nothing to do with the environment. Just has to do with the agent's own random generation of actions in the past. Okay. And in the agent I'm going to propose today, the only algorithmic state is time. Okay, so the agent will be keeping track of how long it's been operating for. The aleatoric state is meant to summarize the agent's situation in the environment. And in the agent I'll describe today, the aleatoric state is updated using some function that is internal to the agent, right? It's part of the agent's design. So there's some function f, I'll call it the aleatoric state update function. And the next aleatoric state is generated by f as a function of the previous aleatoric state, the previous action, and the current observation, okay? So the agent can internally update its aleatoric state as it executes actions and registers observations. Now, the epistemic state is meant to represent the agent's knowledge about the environment. Right? It's what the agent's retaining that's meant to tell it what it knows about the environment. Okay, and our agent is going to maintain an epistemic state with two parts. One is an action value function. The action value function, Qt, maps the current aleatoric state and the current action to a prediction of value. So it maps that to a real number. Okay, so as an action value function, some people call it the Q function. Right. The second part of the epistemic state is a set of counts maintained by the agent. Right. The agent's going to keep track of how many times it's visited each state action pair, and by state there I mean aleatoric state action pair. Okay, so those are the two parts of the epistemic state, and everything that the agent maintains in memory is identified by these three components. All right, maybe I'll pause there for questions. Any questions? Yeah, okay.
There are no questions in the chat box. Maybe I'll ask a question. So
Sure.
Can you tell more about what the aleatoric state is? Because normally when you can, in simpler settings, that's actually the real state of the environment, right? But here, what you're saying is that it's something that the agent believes in. It's not, it's something simpler than the environment.
Right, right. It's in the mind of the agent. Right? It's part of the agent's thought process. It's not related to the environment. And I think it's important that we get away from thinking in terms of environment state, right? If we want to deal with very complex environments. Yeah, so I'd say that, you know, in an area like, say, operations research, there's a constructivist approach, constructionist approach to research, where you have a model of the environment, you take it very literally, and you try to find the best solution for that model, right? So this is an effort to try to get away from that and have what some call a constructivist approach, where, you know, the environment could be anything, but these sorts of ways of thinking about the environment are actually in the mind of the agent, right? So this aleatoric state is an example of that. It's something going on in the mind of the agent that may or may not directly relate to what's going on in the environment.
Can I please ask also a question about the model?
Sure.
So this state, this epistemic state, this description, calligraphic S and A, they don't depend on time. So what depends on time? Is it a different function at every moment of time? Where is exactly time dependence?
You're saying why is the epistemic state PT depending on time, right?
Yeah, where is exactly the time dependence?
Yeah, I haven't given, when I define the agent, you'll see how QT and CT are updated, right? QT and CT will be updated based on the aleatoric state and the observation, right? So
they will be different functions. They will be different functions at different moments of time.
Correct.
Okay, that's clear now.
Correct,
yes,
correct.
Thank you.
So here I'm just defining the domain and range.
Yes, great, thank you.
All right.
I have another small question. So, so this epistemic state depends on the whole history of the observations, right? So,
well, it gets updated, yeah.
so
every
is this model still Markovian? How will the transition probabilities look like? I don't.
That's what I'm saying. We're trying to get away from transition probabilities. I don't want to be modeling transition probabilities here, right? So the agent will have in memory, all it has in memory are these elements, right? It's going to keep track of how long it's been since it started. It's going to keep track of the aleatoric state, which is going to be updated exactly as shown on this slide. And it's going to keep track of an epistemic state. And I'll describe how the epistemic state is updated when I describe the agent.
Okay.
Can I ask a question? Is the function f chosen once and for all? You're not learning the function f.
Good. So I think that the agents of the future should learn the function f, right? But for the agent I'm going to describe today, the function f is fixed. All right? I think maybe I should continue. Okay, so let's talk about policy classes. There's really three classes of policies we should be thinking about to understand how this agent operates. There are policies that map history to action. There's policies that map agent state to action. And there's policies that map aleatoric state to action. Okay, if a policy maps history to action, then the probability of AT, condition on history, is given by that policy. And you need the history in order to take that action. And I'll call that class of policies P script. The policy maps agent state to action. The probability of the next action, condition on history can be generated by the policy, and thus it really only depends on the agent state xt, okay? And policies that map aleatoric state to action, this class P tilde, select actions just based on the aleatoric state, okay? So the action depends on history only through the aleatoric state. All right, let's talk about rewards. So I'm going to think of rewards in terms of a reward function that characterizes the designer's preferences, the agent designer's preferences. All right, so the idea is at each time t+1, the agent can assess how much it likes what it sees. And it's going to do that through a reward function, R, that assesses reward based on the current aleatoric state, the current action, and the realized observation. Okay, and as I discussed earlier, the aleatoric state is updated by this function f. All right, so all of this is going on in the agent's mind. It has nothing to do with the environment necessarily. Okay, so one thing to note about these rewards is that they depend on history only through the agent state and the immediate observation. All right, and we're going to think of performance in terms of average reward, or eventual performance in terms of average reward. And the average reward for a policy pi from any of the three classes I described earlier can be, we're going to define this way. It's a limit of the expected average reward. Okay. All right, so I described classes of policies, and now let me talk about particular policies of interest. One is the optimal policy, right? That's the policy that's allowed to select actions based on all of history and is optimal among such policies. Okay, so we'll call that the optimal policy. I'll use notation lambda star as the optimal average reward. So it's the average reward for the optimal policy. And then there's the agent policy. This is, you can think of this as the agent's algorithm, right? The agent generates actions based on agent state. And the agent policy describes how those actions are generated, right? And that attains some level of average reward, right? We'll call that lambda pi agent, right? The average reward for the agent policy. Finally, another construct that we're going to use is a target policy. A target policy is a policy that selects actions based only on aleatoric state. Okay, and there's an optimal or there's an optimal policy of that kind, and we'll call that the target policy. Okay, and the average reward of that is lambda pi tilde star. Pi tilde star is the optimal policy among those that generate actions based only on aleatoric state. We call that the target policy. Okay, so one way to think about this is, the agent policy is what the agent's actually doing, and the target policy is how well the agent hopes to eventually work. Okay. All right. So let's talk a bit about the agent initialization and operation. And so the way to think about what I'm going to tell you is, suppose I give you a piece of software that represents this agent, right? I'm going to talk to you about, how to initialize that software and then how to apply it. Okay. So we're viewing the agent here as a black box, and we're sort of thinking what it needs from you in order to apply it. Okay, so to initialize the agent needs a few things. It needs a set of actions, right? So, that's a set of actions associated with the environment to which you plan to apply the agent. A set of observations that can be registered from that environment. A set of agent states. An agent state update function. An initial agent state. You got to initialize that agent state somewhere before you see anything. And a reward function. Okay, those are the only inputs required to initialize the agent. All right, and then once you've given those agents, the agent those inputs, you can, let it loose on the environment. And so long as, the set of actions and the set of observations correspond to that environment, the agent can operate in that environment, and you can see how the agent does. All right. The agent follows some policy, right? The agent generates action somehow, and that's what we call the agent policy. All right, so that's how the agent operates. All right, so let me talk a bit now about how the agent performs. And note that I haven't told you what's inside the black box yet. Right now, I'm just telling you performance guarantees about that black box. Okay, and we'll assess performance in terms of regret. And I'm going to define regret here as the expected sum of differences between the optimal average reward and the realized reward. Now, note that the optimal average reward is optimal across all policies that can depend in any way on history. Okay, whereas the agent is much more limited because it's bounded by memory and computation constraints. Okay. All right, let me go back a bit. Any questions about this?
Yeah, I had a quick question. So your reward function depends on the agent state, and more often it depends on some true state of nature. And does it matter that you define it this way?
Yeah, so the philosophy is the designer has to decide what it wants to see from the environment, right? And And part of that design, right, is in choosing agent state dynamics and a reward function that reflect the designer's preferences. That make sense?
I'm thinking of a Kalman filter as an example. So if you are not tracking the state well, then how do you define the reward purely in terms of the agent state rather than the, I don't know if this is a good example to think of.
So I think you're thinking of reward as exogenous, right? I'm thinking of reward as the designer's preferences that get encoded in the agent. So if you have to track the system well in order for the designer to accomplish what it wants to accomplish, right? Then you need a richer agent state, a richer aleatoric state. Right?
Okay.
But the idea is, in order to operate in your life, right? You may not need to track the details of everything going on in every city across the globe. Right? It may be sufficient to track something much simpler, right, in order to generate a desirable outcome over your lifetime.
Okay.
That makes sense?
Mm-hmm. Thanks.
I have a question about lambda star here. Is it some sort of long run average optimal, or does it depend on the horizon t?
Long run average optimal.
Okay.
Right. And the way to think about what we're doing here is capital T is going to be very big, right? And our priority is to get good long run performance, but we'll also look at how much data it requires to get us there.
Yeah, so is it necessarily summable? It might be not summable. Is it important?
So good. So I think my discussion of averaging times will address that. That relates to your question about summability, but I'm going to look at it in terms of averaging times. Okay. Okay, and this is actually the next slide. So this concept will play an important role in understanding how well an agent like this can work. Okay, so the agent has to quickly assess and compare policies, right? In a sense, an agent can only operate in the world if it can do A/B testing. Okay, so the question comes up is how long is required to ensure that you can compute an average within some tolerance epsilon. Okay, so suppose the agent decides, I'm going to use some policy. Well, how long will it take the agent to figure out how well that policy is working? And we want a concept that allows us to quantify this averaging time in a way that applies across all histories. And we want to sort of say that there's some tau pi for given a policy pi, there's some tau pi where if I want to get my assessment of the average to be within epsilon of the long run average, right? Time, tau pi over epsilon time steps will suffice. All right, so I think this is an important concept. Tau pi is sort of characterizing how long it takes to compute an average in the setup. And we'll call tau pi the reward averaging time of policy pi. And here's the definition that serves this purpose. Okay, but I won't go into all this notation, but it's really defined to capture the concept we're after here, which is within time tau pi over epsilon, we're always going to be able to compute the average reward of policy pi to within tolerance epsilon. All right, so that's an important concept that we'll use. Another concept that will come in here is discounted value. So most of you, I imagine, are familiar with this, but to clarify, discounted value of policy pi, v pi gamma h, with discount factor gamma, is the expected discounted sum of rewards discounted with the discount factor gamma. Okay, and here, clearly the discounted sum of reward is going to be a function of the history. Okay, now one thing to note here is, gamma is effectively defining a horizon of interest over which we want to attend to future rewards. And you can think of the effective horizon of interest here as 1 over 1 minus gamma. All right, so there's also this concept of optimal discounted value. And the optimal discounted value function, V star gamma, is arrived at by taking the supremum over pi over all policies for each history h. Okay. All right, let me talk a bit about predicting discounted value. So you can think of aleatoric state as inducing a state aggregation, right? For any history, by using the aleatoric state update function applied incrementally over that history, you arrive at a current aleatoric state. Okay, so there's a mapping from history to current aleatoric state. Okay, let's call that S of H, the current aleatoric state given history H. And you can think of that as an aggregation induced by the aleatoric state update function. And one thing of particular interest to us is the set of value functions that predict value based only on the aleatoric state. So remember, to predict value, discounted value perfectly, we need to take into account all of history. So you might consider, gosh, what if we predict value based only on aleatoric state? Okay. Now, if you try to predict value based on aleatoric state, you're effectively partitioning the set of histories. Okay, so that you can think of this orange ellipse as a set of possible histories, and in there is our current history H, right? And by trying to make a prediction based on aleatoric state, we're saying, gosh, all histories with the same aleatoric state have to generate the same prediction. And so you can think of all histories with the same aleatoric state as making up a cell of this partition. And so two histories, H prime in the same cell, give the same aleatoric state here. And if we're trying to predict value based on aleatoric state, we're going to generate the same prediction for both H and H prime. Okay, so if you generate predictions based only on aleatoric state, there's a set of representable functions. I'll call that V script. And these are the value functions that generate predictions based only on aleatoric state, right? And I'll define a term, the fidelity of our aleatoric states. The fidelity of our aleatoric states is the, okay, so let's start with this part. Here I'm taking for fixed gamma, I have the optimal discounted value function for that gamma. And I can look at the difference between that and some prediction of V tilde. And I can take the infimum, which gives me the best prediction, the best set of predictions with respect to the sup norm, the best set of predictions if I'm predicting only based on aleatoric state. Okay? So you can think of this term as the best I can do with respect to the sup norm if I'm generating predictions based only on aleatoric state. And then what I do here is I say, gosh, there's not one particular discount factor that I care about, but really I want to do this well over all sufficiently long discount factors. And so I'm going to take a supremum over discount factors that have, so over all sufficiently long horizons. So I'm going to take the supremum over discount factors that identify sufficiently long horizons. Okay. Now, what's a sufficiently long horizon here? Well, I'm saying horizons that are longer than the reward averaging time of the target policy. That is the optimal policy among those that generate actions based only on aleatoric state. Okay, so basically here we're saying we only care about very long horizons longer than required to compute average reward for the best for the target policy. And I'm going to take the supremum over those. All right. Maybe I'll pause there for a quick question if there's one.
And I had a question. So somehow the distribution of H condition on the aleatoric state also matters here. So is there some consistency issue when you say V is a function of S, like that the policy should somehow induce the distribution of H within condition on S so that somehow...
This H is not a random variable. This is a dummy variable, right? I'm using, so HT is my random variable.
Mm-hmm.
Right? This little h is a dummy variable. Okay, so here I'm thinking, h is in some set of possible histories. And I'm defining another set, V script here based on that. So there's no probability going on here.
Mm-hmm. I see. Okay. Thanks.
Thanks for that. Yeah, I should have mentioned I use capital letters for random variables here, but lowercase for dummy variables. All right, so here's a regret bound one can prove about the agent I'll describe. And there's really three terms in the regret bound. One is what you might think of as a persistent term. So if the right-hand side grows with capital T, that means there's some loss induced in every time step. So this is something that will actually impact our eventual performance, right? It'll cause us to make suboptimal decisions, permanently. The second term is transient. So this is a term that where we'll incur regret over time, but eventually the amount of regret incurred per period, per time step, will go to zero. Right? And there's this third term, which I just won't talk about because that's going to be dominated. The other terms are much more significant than this one as time increases. And so I'm not going to worry about that third term at all. All right, a few remarks that make this regret bound interesting to me. One is there's no dependence on the number of environment states. Okay, there's no dependence on how complex the environment is. There's no dependence on the the environment dynamics, the complexity of that. Also, the per period regret satisfies this quantity, which is kind of interesting. So this is like looking at the long-term difference between the average reward attained by the agent and the average reward attained by an optimal policy, right? That's bounded above by 15 times delta, right? Delta is the fidelity of our aleatoric state. And so, so the fidelity of our aleatoric state here is controlling how well this agent eventually performs relative to an optimal policy, right? And remember, the fidelity of the aleatoric state, limits how well the agent can predict future value. And so it sort of makes sense that there's this relationship. Yeah. Let's talk more about this asymptotic performance. As I mentioned, we have this asymptotic bound. So there's a paper I wrote in 2006, which in which one result implies that this asymptotic bound you can't do any better than 2 delta, right? That's a fundamental limit, right? And so it seems that we're within a constant factor of the best we could hope for with this kind of result. And interestingly, this is the first algorithm I know of that's able to come within a constant factor. right, that's able to get a linear bound in delta among all algorithms that use reinforcement learning or approximate dynamic programming. And by approximate dynamic programming here, I'm saying, I'll tell you everything about the environment. So you know everything about the environment. You're allowed to use all that information, right? And suppose I ask you to come up with a policy that comes within a constant factor in this way. I haven't known of any other algorithm that can efficiently achieve that, even if you have all information about the environment. And so it's interesting that this reinforcement learning algorithm is able to achieve that. And other, approximate dynamic programming methods that are known to be tractable and give decent results end up making the right-hand side grow not only with delta, but only with some notion of mixing time, perhaps a mixing time of the environment. Okay. All right. Let me talk about how long it takes us to get to this eventual performance. Okay, and for this purpose, let me characterize what I mean by an epsilon learning time. Okay, an epsilon learning time, T epsilon, tells us how large T has to be so that our average regret is dominated by the eventual average plus epsilon. Okay, so it's sort of how long it takes to come within epsilon of eventual performance. Okay, so our regret bound implies a polynomial bound on this. So the epsilon learning time is polynomial in the number of aleatoric states, the number of actions, the average time of the target policy, and 1 over epsilon. Okay, so that's an implication of our regret bound. And the most interesting thing here, I think, again, is that this doesn't depend on complexity of the environment, except perhaps if that complexity impacts the averaging time of the target policy. And intuitively, it seems like it should be, since the target policy depends only on aleatoric state, typically you wouldn't expect that to be driven by the environment complexity.
Hey, Ben, quick question. Does epsilon have to be larger than constant times delta here? Or?
No.
Okay.
Okay, so in fact, the environment mixing time could be infinite. So one thing we're trying to avoid here is any notion of environment mixing time coming into play. All right, now special case of this is where aleatoric state equals environment state. Okay, so suppose you define your aleatoric state to represent all the complexity of the environment. There's large literature on that special case, really spearheaded by the Kern-Singh paper from 2002, and a lot of subsequent work on that goes under the tagline of efficient reinforcement learning with tabular Markov decision processes. And so this is all very interesting work, but so far it's really focused on the case where aleatoric state captures everything about the environment state. And I should mention that a recent paper in this line of work presents an algorithm that is very similar to the agent I'll present, but really only studies it in the case where aleatoric state is equal to environment state. And that's his recent paper by Wei and others. All right, so let me describe the agent now. Okay, so the agent uses an optimistic version of Q-learning. And just to remind you, here are the inputs required to initialize the agent. Among other things, as I mentioned, the agent keeps track of an epistemic state, which is comprised of an action value function and state action counts. And here's how optimistic Q-learning works. The agent repeats a number of steps over and over in each time step to generate the next action. Okay, so the way it's going to generate the next action, it's going to take a greedy action. Okay, it's going to take an action from the set that maximizes the action value function. Okay, so QTSA is its prediction of future value given state S and action A. And basically, we just want to choose an action that maximizes that. But in order to define this clearly, let's say we uniformly sample across such actions. And then there's the agent state dynamics. The function f was provided to the agent upon initialization, and so the agent can compute its next aleatoric state st plus 1. Okay, given that it just executed the action at and the environment supplied the observation ot plus 1. Okay, then I want to update the epistemic state. And first I'll initialize the next epistemic state by taking the value function and the count to be identical to what they are now, but I'll modify them in the next steps. Okay, so the counts I'm going to modify by adding 1 to the count of the state action pair that I just observed. And the action value, well, I'm only going to update the action value for the state action pair I just observed. And I'm going to update that by taking a convex combination between two terms, one being the previous value for that state action pair, and the next being a new estimate, little q. And little q is computed by this quantity where I add the immediate reward RT plus 1, which I've computed using the current observation, current aleatoric state, and add that to the discount factor gamma times the maximum value of the next action. So it's just Q learning, but maybe what differentiates it from Q learning is that I add this optimistic boost, which involves a parameter beta divided by the square root of the counts of that state action pair. Okay, so I'll talk about these parameters gamma and beta more later, but there's some parameter gamma and beta I'm going to use within the agent to update the action values, and I'm going to update the action values in this way. I'll also have to define what step sizes I use, right? Alpha is a step size that depends on the count, and I'll also discuss that a bit. All right. So, so that's the essential optimistic Q-learning algorithm. And in order to get the regret bound I've supplied, what I do is I start with all the counts initialized to 0. And all the action values initialized to 1 over 1 minus gamma. Right? And I use this step size sequence. It's a specific step size sequence. So, that defines a step size for each k, right? I'll plug in for k the count whenever I use a step size. And I'm not going to go into the details of this, but what you have to do to get that regret bound is once in a while, you increase the discount factor and increase beta a bit. And when you do that, you reset QT and CT, letting the counts be 0 and the action values be defined by the current discount factor again. Okay, so once in a while you reset and you increase the discount factor and this optimistic boost coefficient beta. Okay, I'm not going to describe the details of those resets. All right, but with all of that, you get the regret bound I described. Okay, so this is optimistic Q-learning, and it gets that regret bound. This is the agent. All right. So I thought I'd close by discussing some open issues in this area, and there are a lot, as you will see. Okay, so first, with regards to the specific agent, and perhaps variants of it. There's a lot of work to be done to improve this bound. For starters, even the eventual performance bound seems loose. And one question is whether we can match the fundamental limit, get that 15 down to 2. Yeah. Further, the transient part of the bound is very loose, extremely loose. Also, the agent is not great. There's so many ways one could improve this agent and possibly improve the bound alongside that. In particular, t to the 4/5 looks really bad. And I think even for this current agent, we can probably improve that. But there's probably lots of tricks one can bring to bear to improve that further. And an agenda I'm particularly find exciting is, there's this big universe of tricks of the trade in reinforcement learning, practical tricks that reinforcement learning agent designers actually use when they design practical agents. And an interesting thing is to try to bring these tricks into the mix and see if those tricks can lead to improvements in this bound. All right, now there are many other directions one can consider. So over the weekend, we posted a new paper on arXiv that develops an interface between reinforcement learning and information theory. The hope is that this offers principles for more efficient and practical agent design. The theoretical advances are needed to make progress in that direction. Okay. The agent we described learns from rewards. However, observations in a real environment can present much more information. And to design a data efficient agent, it's really important to learn from more than rewards. One approach to doing this involves learning general value functions, which predict statistics of future observations other than rewards. And I think there's a lot of promise in that direction. Another topic at the frontier of this area involves tracking. In particular, rather than aiming to converge on some target policy, it may be possible to significantly reduce regret by targeting different policies under different circumstances over time. Okay. So in particular, with an agent that is much simpler than the environment, it seems like that ought to be beneficial. Finally, the agent we've described aims to attain high average rewards, but the algorithm we use is really for discounted rewards. So there are versions of Q-learning that aim directly at maximizing average reward. And an elegant instance of this is in this recent paper by Wan, Naik, and Sutton. Perhaps there's more elegant and natural approaches than our current agent that leverage some kind of average reward Q-learning. All right. And for these sorts of things, I think we really need a lot of help from people who know probability, and I think this audience is really primed for that. All right, finally, just to close, I thought it'd be interesting to talk about a philosophy underlying how reinforcement learning work is motivated. So in a sense, reinforcement learning has pushed toward abstraction away from simplified models of specific environments. One motivation for this is what Rich Sutton calls the bitter lesson. He actually has a blog post on this topic if you're interested. The premise is that problem solution methods become obsolete within a decade if they don't scale with data and computation. As an example of this is the success of deep neural networks, which offer tools that can scale with data and computation where statistical methods designed for specific data set sizes and computational constraints may not. Based on this premise, a natural extrapolation from where we are today is toward methods that abstract away from stylized models and generalized across data from different problems. For example, instead of designing an agent for controlling a queuing network, you might design an agent that can simultaneously be applied to a number of environments, or you can think of it as being applied to all those environments just at different points in its lifetime. So it could be applied to dialogue systems, it could be applied to the internet. And the idea is that by learning from all these problems, all these domains, and generalizing across them, you might be able to do much better than really focusing only on stylized models for one domain. All right, that's it.
Let's thank Ben. Floor is now open for questions. Okay, I'll start with a question. So I'm a little confused about the fact that F and R are given to the agent. So this is the environment, and the environment is doing its thing. It's running its MDP, and it's giving rewards. So I would imagine a natural goal would be to maximize the rewards that one is getting from the environment. But instead, the reward function is like defined by the agent. So what does that even mean?
Got it. So I think you're talking about the Sutton-Bartow book, right? And in the Sutton-Bartow book, let me go back a bit. I can't find this. I'm finding the place where I talk about the reward update.
Mm-hmm.
But in the Sutton-Bartow book, the reward is dictated by the environment.
Mm-hmm.
I'm taking more of a, Van Neumann Morgenstern or Oskam Aumann kind of view of reward here, where the reward is expressing preferences of the designer, right? And so the environment is producing observations. The environment is not telling the designer what he wants to do. The environment is producing observations. It's up to the designer what he likes or what he doesn't like, right? All the environment is generating are these observations.
Oh, I see. Okay.
So sort of more like economics, where you don't say, hey, the economy is giving me a utility function.
Mm-hmm.
Utility function expresses my subjective preferences.
I see.
And the economy is doing what it's doing.
I see. Okay. Okay. And just to get a clarification, the environment, is it still assumed to be an MDP?
I've listed all my assumptions. There was no assumptions about the environment.
So the environment, so the agent applies action on the environment and the agent gets an observation. So how are these observations generated by the environment?
I make no assumptions about that.
Oh, I see. Okay. Okay.
But that's the point here. You want to design an agent that you can let loose in a real environment. And we don't want to take this constructivist view where we have a stylized model or some assumptions about what the environment is.
Just on that point, so this tau epsilon captures everything you need to talk about, like stochasticity or something else that the environment has. So as long as you can learn quickly within tau epsilon somehow.
That's correct. Yeah. So the complexity environment drives our bounds only through the reward averaging time of the target policy.
Aha.
Is it reasonable to think of the model like an adversarial model then? So it's more like a kind of approachability result that you're proving?
It could be whatever you want it to be.
Yeah. Yeah.
Now, if you choose an adversarial model, it's probably possible to drive that averaging time to be very
Yeah.
large.
I was thinking of it like adversarial queuing, where you say, there's only a certain amount of stuff that's allowed to happen in a certain time window. And so that's sort of like your mixing time bound. And you're saying, provided that holds, then we're kind of good and it will approach the policy I want.
That's right.
Add a quick other, oh, sorry, yeah, you go.
Oh, sorry. Do you want to go? You can go first.
No, it's more of a kind of quick token question, but you had aleatoric states, but you didn't have aleatoric actions, and actions could be quite big as well. So would that involve a separate framework where you want to abstract the set of actions, or?
Good. So I guess I think there's a lot of interesting work to be done to deal with intractably large action sets. One perspective one could take is that there's something else that translates the set A script, which is sort of small enough for the agent to select an element of, translates that into a much more complex action, right? But yeah, I haven't talked at all today about what to do if the action set is intractably large.
Thanks.
I had two questions. I was wondering if you can give a little bit more intuition about this tau as well as the delta, as in, are there like some natural properties that would, in which, when would I expect tau and delta to be small versus when would it be unreasonable to expect tau and delta to be small?
Yeah, I think that's sort of difficult to characterize. I think all agents use something like that. So for example, the DQN agent, which is this agent that's popularized from its application to video games, uses as its aleatoric state, I think 8 recent frames from the arcade screen, right? And it's sort of saying, gosh, that's all I really need to keep track of in order to figure out what to do, right? There's a mu0 agent, which was described in a recent paper in Nature that's been successful in many problems. And that's considered state of the art. And that actually uses a recurrent neural network to learn an aleatoric state representation, right? So there's many, this is what, aleatoric state is what people are using, right? And so the question is, how do we start to create some semblance of a theory that encompasses that? Now, that said, I think that, this particular agent and these particular regret bounds only represent a starting point, and there might be much better ways to characterize things. For example, delta feels really rigid, right? It's taking the supremum over all histories that give you the same aleatoric. I mean, that's really like loose, right? And so the point here is not that should be the end of this, the last word on this topic, but the point is to at least get started in developing theory that could bridge this gap with what's done in practice.
And I guess my next question is, do you think you can give some intuition for what were kind of technical innovations that were needed? In that, I think the agent itself looks, very similar to just other optimistic Q learning algorithms that have been analyzed for MDPs. But what was the kind of additional, what did you have to do additionally to analyze it for this more general model? Got it.
So there's a few key things here, and I also should mention, we stand on the shoulders of giants in a sense, right? But there's been a lot of work in the area of efficient reinforcement learning. Right. And one paper which contributed a critical idea to this line of thought is this paper by Chi-Jin and Sebastian Bubeck and others. That's sort of, for episodic fixed horizon Markov decision processes, established as a regret bound for optimistic Q learning. Right?
Mm-hmm.
Now, to go from that to this required a substantial amount of work because first of all, we don't use MDPs,
Mm-hmm.
right? We don't have any episodicity, right?
Mm-hmm.
We don't have Markovity, and so some of these concepts we introduced were sort of new and important, like this notion of the averaging time of the target policy. I haven't seen that concept used before, and sort of thinking through that and how to make this analysis work was important. The other important ingredient is this paper I wrote in 2006, which was on state aggregation. And I think that the fact that we sort of were aware of the ideas in that paper was really critical to going from MDPs to this kind of general aleatoric state way of thinking. And there's particularly a critical idea there that has to do with, whether you end up with a mixing time times delta, or just a constant times delta. Okay, so there's a lot of work that went into getting rid of that mixing time. Like if you read old papers on state aggregation, for example, Ward Witt has some, but many other people have some. And then if you look at the kinds of bounds they have, it's always involves like mixing time times delta effectively, right? So the issue is how do you get rid of that and just have something that depends linearly on delta.
I see, thank you.
Sure.
One question I have is why do you occasionally reset the Q value in the algorithm?
I'm sorry, I can't hear you.
Why do you occasionally reset the Q value in the algorithm?
Now I can hear you, but I'm not quite understanding. Why did I what? Sorry.
Why do you occasionally reset the Q value in the algorithm?
Reset.
Yeah.
Good. Yeah. So that's another really synthetic element of the algorithm that should not go in a practical algorithm, right? But the reason we occasionally reset is the agent does not know the averaging time of the target policy. Okay? The agent does not know that. And so it can't start with an assumption that only predictions of a particular horizon matter, because it doesn't know what that horizon is. Right? So what it has to do is it has to continually increase its prediction horizon over time, right? So that whatever the right prediction horizon is, it'll eventually get there, right? And so 1 over 1 minus gamma is the effective prediction horizon, and that needs to be increased over time.
Okay, thanks.
Well, thank you very much. These were great questions and stimulating audience. Thank you.
Let's thank Ben again.
All right, well, thanks, guys.
Ben, could you point to the paper for this talk? There's something on archive, but it doesn't seem to have the same result in the abstract. So I was just wondering if...
Got it. Okay, so there's actually 2 papers I recommend looking at. One is the paper with Xidong and Zheng Yuan. And there's a version in archive, but it's been updated to be more consistent with this talk. And the updated version should appear tonight. I think she probably uploaded it last night. That's number 1. And number 2 is the information theory paper, which you put in archive, I think on Saturday. So hopefully it'll be available soon.
Okay, sounds good. Thank you.
Sure.
Ben, I was wondering, is there like any relationship to POMDPs, or in that there's kind of, an observable state and the hidden part? But I guess is a difference that, there's still definitely more assumptions in POMDPs than you're making.
Right. So I find POMDPs not to be particularly productive to think about because they just introduce so much complexity into the thought process. But yeah, that's an alternative way to think about this, right? As there exists some environment state out there. I'm trying to represent my uncertainty about it. You could think about things in those terms. Yeah.
Would them POMDPs kind of translate to some kind of bound on your tau and delta here?
You could pose that question, right? Like if I have a POMDP model of my environment and there's particular characteristics of that POMDP, what would that imply about the reward averaging time? I think that could be interesting to generate some intuition about that reward averaging time.
Yeah, no, it's very interesting. Yeah, just trying to wrap my mind around this properties. Yeah, thank you.
Thanks. All right, guys. Thanks very much. Bye-bye.
Bye.